Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the tutorial on using the academic edition of Liquid. We're going to start by going to the website on GitHub, github/msr-quark/liquid, which is where all the examples, all the documentation, and all the software exist. Before running the tutorial, you should go to this site and go down to the How Do I Get It, which will give you a Getting Started page on how to install all of the pieces, all the prerequisites. One of the prerequisites is Microsoft Visual Studio Community Edition, which is free and available for download, but this will let you program, compile, and run applications that you build with the Language Integrated Quantum Operations Simulator, which we also call Liquid. After you've installed Visual Studio, the next step would be to download the zip file from the website. The zip file will be in your Downloads folder. In this case, it will be called liquidmaster.zip. And as part of the installation, it will tell you to take LiquidMaster, extract all the pieces, and put them into the C: directory, which is what we'll do. The only other step you need to install is to take the liquid-master directory that's created and rename it to Liquid. So if we take a look, we will see that we have a liquid-master directory, and we'll rename that to Liquid. The reason for this is some of the software will be looking for files, specifically the LaTeX compiler will be looking for the file liquidtixz.tech in C:liquid, and this saves you having to rename a lot of other things. So now that we have this, let's take a look at the file tree. There's a binary directory called bin. This contains the executable and all the support libraries necessary to run the system without doing anything else. The docs directory contains compiled help information. This is all of the API documentation, as well as a 100-page user's manual, which you can step through after the tutorial and will show you all the different capabilities of the system. The image directory is just used for pictures used in other documentation. The samples directory contains all sorts of things that run in the system, pre-built, quantum chemistry examples, web graphs, and various other things. We'll spend some time here in the tutorial. And then there's a source directory. This is where you can build your own version of Liquid with your own pieces on top of it. So what we're going to do is we're going to start by walking down to the Windows button, right-click on it, and select Command Prompt. This will give you a new command prompt that we're going to go to the top of the tree, which is C:liquid. As you'll see, everything is there that we were just showing. And what we're going to do is make sure Liquid is running okay. So we'll go into the binary directory and say Liquid. The first time we run, Liquid is going to come back and tell us that we haven't accepted the license. All you need to do is type a capital Y, hit Enter, and it will say thank you for accepting, and you'll never see it again. So this time, if we run Liquid, we'll get a whole bunch of output. We get the copyright notice and also the website to go to for anything you need with Liquid. It also gives you a warning that you haven't registered this copy. Registration really just involves going onto the website, signing up on the listserv, and just saying you're using the software. We're only using the listserv to announce changes, things available with the software, and it lets us justify doing the work on the system because when you install, we get credit that this many people have installed the system and we can continue working on it and we get funding. So I strongly suggest that you register on the website with the listserv, but if you don't, all you'll do is just get this little message every time you run. There are a large number of tests built into the system. We'll go through a few of them as part of the tutorial, but they're all documented in the user's manual. And then there's a usage statement, and finally, Liquid's complaining that we forgot to provide at least one command line parameter. So let's do that. We'll run Liquid. All the built-in examples start with 2 underscores. So I'm going to say underscore underscore sure. We're going to do factorization of the number 21. And I'm going to do it without any optimizations. We're just going to run the circuit. So we'll say go. And now we're off and running. This is a 10-bit value to do a 5-bit number. 10 qubits are needed to do 5. And what you'll notice is we're getting all zeros coming back out. This is a perfectly legal answer for sure, but it also means that we're not actually factoring. So we'll try it again. There's actually a 96% probability of a random result giving you a factorization, but only a 43% for sure. These numbers get much better, of course, as the numbers get bigger, and the number 21 is a fairly small number to factor. But it's a good example, and now you can see we're actually getting some bits back from the quantum operations. So we're running the example through. We're taking a 5-bit number. It's taking us a total of 13 qubits to actually do the circuit. This is Beauregard's algorithm for solving Shor. And when we get to the very end, we got one more to go. You'll see that 21 is indeed 7 times 3, that we got a quantum result of the number 341, and when we do the classical post-processing, that gives us the factors. So we were able to factor 21. Cool. Now we're going to try a little larger number. So like what we do the same thing we just did, Liquid, Shor, and now we're going to go with the number 63. So everything looks the same, except now we're not getting that first bit back very quickly. In fact, this is going to take a long time to factor, and we probably don't want to sit around waiting for it. There's our first bit, just came in. We should notice that at the very beginning of every line, there's a number and a colon. This is the thread number that the message came out on. And then the next digits represent minutes. So this is 0.4 minutes have gone by so far. So 24 seconds. And you will see this on every line, so you have an idea of how long things are taking to run, and you get an idea of, if you have multiple threads, where the messages are coming from. So we're not going to wait for all of this. We're going to be a little smarter. We'll take this and say, I'd like you to optimize the circuit. So now what you'll see is we started with 28,000 gates to factor the number, and we compiled this all the way down until we only had 1,200 gates or matrices that we have to multiply, and you can see the difference in the speed. We're running all the way through. Of course, again, sure, every once in a while we'll return 0 for a result. So let's start them again while we're talking. And there we go. We're starting to get some bits back out. But this now runs very quickly. The simulator has a large part of it devoted to optimizations for the classical simulation of quantum systems. This makes it very quick to operate on fairly large circuits with fairly reasonable numbers of qubits. And sure enough, 63 is 9 by 7. So we've just factored a number bigger than any of the numbers normally published for sure. And this is just the beginning of how big you could go in the system. So that's a quick overview just to show that the system runs, you've got everything installed. Let's take a little more time looking at other options by using another example called teleport. Again, we'll call the teleport function by using 2 underscores and then the word teleport. Case does count and 2 parens. And when we go to run it, we're going to get 3 sets of runs that come out one after the other. The first one, we're just calling all the functions in teleport directly. The teleport function takes a qubit state that happens to be randomly chosen and then transmits it to another qubit quantumly, provided there's 2 bits of classical information that are discerned. We're actually going to look at the circuit after we're done running it here and show you what it does. But we ran it several times with different random numbers, and we always get the number successfully teleported depending on whatever bits came out on the other end. We're then going to draw the circuits. We'll take a look at what the drawings look like, because instead of a function call, we're going to pull all the data back from the functions and create a data structure called a circuit. When we run that data structure through the system, we get the same answers again. So everything works well. And then we're going to optimize the data structure. In this case, we've reduced a very simple circuit, 8 gates to 5 gates. We run it again, and again, teleport still works. So the good news is that all of this works fairly straightforwardly. And as I said, we generated some drawings while we were going. Let's take a look at the drawings. If I look at teleport and just look at the normal circuit, we have an HTML file generated. That's an SVG drawing. And if we take a look, we can see we can label the qubits. We can put the various gates down on the system. Everything flows from left to right. This was our source that we started with. This was the destination we got out. These are the 2 classical bits that were generated, and then the gates that were applied based on the classical bits. So this makes it very easy to generate drawings on the system. We can also make it a little prettier. If you notice on here, you'll see that there's 1 gate per unit time. We really don't have to do that. Instead, we can fold this. This was another output that we generated. And now you see we line the gates up a little better. It's a little prettier drawing. And it also shows you what can be parallelized in the system fairly quickly. We can also look at the version that we optimized, or we grew the gates together. And now all the gates at the beginning have been combined into a single gate, which is a 3-qubit gate, and then we have to measure and apply the output. So this gives us some very simple drawings very quickly. We can also get much higher quality drawings. If we go back to that CF version, there was also a LaTeX version generated. If you install MikTeX and anything else on top of it that would edit, in this case TeXworks, this is the file that was generated by Liquid. And if we ask it to compile it and render the result, here's what we get. So we can get publication quality graphics very easily, and of course the file is fairly easy to edit if you want to add your own annotations or changes to it. The system is able to draw everything by using a LaTeX package we wrote called liquidtixz, which is sitting in C:\liquid. And so that's why the first line of the file referenced that file, and that's why we put everything in the liquid directory. One of the reasons was so that LaTeX could find the files. So now let's do some programming. First thing I'm going to do is open up the directory, and I'm going to go into liquid source. And this directory is set up to be run with Visual Studio Community Edition, which you should have put on your machine. And the very top of a project or of a application that you're going to build is called a solution file. And here's a liquid.sln or solution file. And this solution happens to have one project on it, also called Liquid, which is an F# project. If we open the solution file, Visual Studio will open. And it's making sure, since we downloaded this from the internet, that we're sure we want to do this, and say, yes, we do want to open this file. We know it's okay. And what we're going to see, I happen to like a dark background, but you can set the backgrounds you like, is in the Solution Explorer, these are the files that were in the directory, and the one that we want to work in is called main. So I'm going to double click on it and open up main. This is a nice little prototype file you can edit, add your own applications to, and work. At the very bottom of this file is a module called app, which has an entry point for the entire application called main, which runs liquid. And this is actually what gets executed every time you say liquid to the command line. We're going to edit a little function here, a sample function called userSample. Again, we just put the 2 underscores to flag that this was something we were doing as an example. You don't need to use the underscores. But what we did is, before we created this function, in front of it, we put an attribute. And what this attribute, LQD, does is says the following function should be callable from the command line. So we're going to try and see how this works by first building our own version of Liquid and seeing that userSample works. So I'm going to go over to Liquid, which is ready to go. I'm going to go up to Build, and I'm going to say Build the solution. And so in the output window, we can see the solution going by. And the build succeeded. And if I now say start the application, the application will start up, run Liquid, and for some reason we're running Shore. Now why is it running Shore? We have to tell Visual Studio that we actually want to run userSample, not run Shore. So I'm going to right-click on Liquid, go to Properties. And for one thing I'm going to do is I'm going to say, let's change debug mode to release mode, because the code will run faster. We're not actually debugging at the moment. But debug is how it gets told how to start things. So I'm going to tell it, instead of Shore, run underscore underscore userSample. So this is just what you would put on the command line after saying liquid.exe. And if I now say build, and actually I'm going to show you a shortcut. You can build the solution and then you can debug it and run the solution. It turns out Control F5 will build the app, start the app, and run it. So from now on we're just going to hit Control F5, which will see build and run. But now the application built, it runs, and it says this module is a good place to put compiled user code, which is the line we had in userSample. If you notice, userSample is using command show. This is part of the API for Liquid. Show really is an alias for printf, and all the same arguments for printf will work. The difference is it adds a new line at the end automatically. It also is thread safe. So if I do shows from all over the application on different threads, they won't write on top of each other. You'll always get clean output lines. In addition, every time you run, you get a log called liquid.log, and everything that you say show winds up in the log. So it's good practice to use it instead of printf, and there's really no reason not to. So now let's write some code. So what we're going to do is take this line and remove it, and I'm going to write a little function here that's going to gather statistics. So I'm going to say stats equals array.create 2 elements and start them both off as 0. So this will give us a place that when we have a single qubit, we're going to measure and either get a 0 or a 1. We're going to put the statistics into here. So to hold our qubits, we need a state vector, and that's created with the ket class. So I'm going to create a ket with 1 qubit, and the k now is a vector that contains a single qubit. For loops in F# are just like any other language. You give it a start, dot, dot, and end, and say what you want it to do. Like Python, everything is indent sensitive. So to go inside the loop, we indented with a tab. And since every time we go around we're going to measure, we're going to destroy the ket vector. So I'm going to tell the ket vector to reset itself back to 1 qubit every time we come around the loop. So this way we have a fresh state vector every time. So what I want to do is call a quantum function with my qubits. Well, we don't have a quantum function yet, so let's add it. We'll go in and say let qfunction of qubits, which is a list of qubits, equals, and I'm going to call a measurement of qubits. Every quantum function ends in a list of qubits. So just like the one we're creating or the one we're calling. M is built in to Liquid, which is just do a measurement, but it does a measurement of 1 qubit. Every function takes as many qubits as it needs off the front of the list and performs the operation. So however many qubits there are, measure is going to measure the first qubit in the list. That's it. We now have a quantum function. After we have the function, I want to see what we measured. So if we go back to that list of qubits, we pull the first qubit off by asking for the head of the list. We ask for its bit value, which is a data type in liquid that knows if he's a 0 or a 1 or unmeasured. And I want to convert it to an actual integer. So I want its value. That'll give me a 0 or 1. And once we have that, I'm going to store away in stats of whichever value that was, stats plus 1. So if we measured a 0, we'll add 1 to the 0 entry. If we measured a 1, we'll add 1 to the 1 entry. You'll notice the dot between the brackets. It's a little different than other languages. That's one of the main things you have to remember in F# is when you access a list or an array, you have to put a dot between the brackets and the variable name. And we'll just show our result at the end of the loop. So we measured 0 this many times and 1 this many times. Again, same as printf. The other thing in F# is arguments are just separated by spaces. You don't need parens and commas. That's it. That's our entire function. I'm going to hit Control F5 to run it. And when we run it, we got 10,000 zeros. Well, it makes sense. We created an empty ket vector, happens to start at 0 if you haven't said anything differently. And when we measured it, we still got 0. Haven't done anything quantumly. Really, we just created a qubit and measured it. So let's change this. We'll go back up to QFunction. And now I'm going to do a Hadamard gate of the first qubit. Hadamard will take the 0 and rotate that qubit to halfway between 0 and 1. So we're now at the 50-50 position. Again, I'm hitting Control F5 to build and run. So now, each time we measure, there's a 50-50 probability of a 0 or a 1, and sure enough, we measured 5,000 zeros and 5,000 ones. We have just done a superposition, the first piece of actual quantum code. So this is all good. Everything works. Now I want to do something more sophisticated. You notice in this file there's another function called rotx. This is a general function that will rotate a qubit around any arbitrary angle in the x-axis. Again, the last argument is always the qubits list. And this looks a little different because what we're going to do is create a gate data structure and then call that gate to run the gate for us. And the reason for this is this lets us do direct function execution, introspection in getting circuit values back, further introspection to get actual matrices and pieces. If it was just a function, we couldn't get the data information back out. So we use one extra level of indirection to make all that work. This is the general form of how to make a gate in Liquid. The gate itself has a name. You can put a help string. Has a matrix that's a complex sparse matrix. In this case, it's a 2 by 2 matrix where the 0, 0 entry is the cosine of the angle over 2. The 0, 1 is the minus sign, the 1, 0 is the sine, and the 1, 1 is the cosine. So it's a general rotation around x. And in unitaries, the angle that you're rotating by is divided by 2. There's an interesting explanation why, but we won't go into it here. And there's a drawing line. This actually is calling our liquidtixz package to say, draw this as a gate, and here's the name I want to put in it. And since this is LaTeX code, you can actually put LaTeX directives and symbols in here, and they will work. So this gives us a nice little gate, and what we're going to do is come down where we had the Hadamard and replace that with the rotate x, and we're going to rotate by math.pi over 2. And run it again. Control F5. And yes, F# is very careful about data types. You have to put a period after the 2 because it's a floating point number. And we got the exact same result. Instead of rotating it one way, we rotated a different way, but we still got to the equator at 50%, and we got a 50% value. Well, now let's make it more interesting. Let's make this pi over 4. When we use pi over 4, we'll see that we don't get 50-50 anymore. Now we get 8531 and 1469. And if you look at this number, it turns out that plugging in our angle, the cosine of pi over 8 squared is 0.85355. So 853 is exactly what we'd expect to see out of this, and the probabilities all work right. Great. However, all we've done so far is superposition. We also want to do entanglement. So what I'm going to do is change our quantum function to do the gate that we're doing already on the first qubit, and then if there's more qubits, for q in q's dot tail, everybody but the first qubit, I'm going to say do a controlled knot, which is an entanglement gate, between the head qubit and this qubit. So at this point, this will now do the first qubit, rotate it, and then entangle it with all the other qubits. Now we actually want to measure all the qubits, and we have a built-in operator in Liquid called the bow tie, which will map a measurement onto all the qubits. We could have just done a for q in q's, do m of the qubit in the list, but this is just cleaner syntax and easy to use, and we'll start introducing some of the operators as we go. So now we have to change our user sample. The command line we're going to change to actually take an integer that is how many qubits we want. We'll change our ket vector from 1 to n. We'll reset it back to n qubits. And everything else will work, but we also want to prove that the entanglement worked. So after we get back the result of the function, we're going to say for q in q's dot tail, again everybody but the head qubit, if q dot bit is unequal to q's dot head dot bit, then fail. This is throwing an exception. Bad. So now what we have is a test that every qubit, after we measured the first one, read the same thing, because they're all entangled, and whatever we do the one qubit will happen to all the others. So we'll run it again, and we'll see what happens now when we run the package. And actually, we blow up because the input string was not in the correct format. The problem is the command line doesn't match what the function says it should be. If we go back to how we're running Liquid, we now have to tell it how many qubits. It's expecting an integer argument. So we're going to put the argument in and run it again. And this time it's running, but notice it doesn't come back right away. Now we rotate the first qubit, then entangle it with 9 other qubits, then measure all 10 of them. These are big operations, and we're doing it 10,000 times. So this is going to take a little while to run. And if we take a look at what's going on, you can see this is on a little surface that all 4 threads were almost at 100% in use. And we got the same answer we got before, but we got no error, so we know the entanglement worked. And this took 18 seconds to run. So this took quite a while. We'd like to move to making this going much faster. So the next thing we're going to do is at the very top, we're going to define a circuit. We're going to call the circuit class and ask it to compile our function. And of course, the function has to know how many qubits to run, even though we're not running the function now, we're just compiling it with Liquid. So we're going to tell it to use the qubits that are in the ket vector. So by doing this, we've created a circuit. What does a circuit do for us? Well, instead of calling Q function now, we can ask the circuit to run the qubits. And so this gives us a way to run, instead of calling qfunc directly, we actually now have built a data structure that represents the circuit we're running, and now we're running it again. But you'll notice it's not any faster. And the reason it's not any faster is we're still doing just as many quantum operations. So the number of vector matrix multiplies hasn't changed. In fact, we might be slightly slower because now we're interpreting a circuit instead of running compiled F-sharp code directly, but it took a little bit longer, 0.4 instead of 0.3 minutes, but we get the same answer. And so this time, we now like to make this more optimal. So once we have the circuit, we're going to create a new one, and I'm going to say to grow the gates. And there's all sorts of optional parameters, but one we have to provide is the ket vector. So he has a state vector to tell him what to do. We take a circuit, and what grow gates does is collapse many of the gates together into single ones. You couldn't do this on a quantum computer, but this makes the classical simulation better. And we're not going to change anything else. That's all we're going to do, is grow the gates. And so we change the optimization. We run the new circuit. And the last one took 0.4 minutes to run. And then this one took something under 6 seconds to run instead, or 0.1 minutes. And again, we keep getting the right answer, so that's always a good sign. So these are ways to optimize the systems that you write. Let's also get some information. What do these circuits actually look like? So I'm going to say, show test 1. And into the log file, I'm going to say, take the circuit and dump it into the log file. So we can actually look at the circuit, see what it looks like. Also, while we're at it, I'm going to want it to draw it. So I'm going to say render in HTML and LaTeX, test 1. So that'll give us some information about the first circuit. And then let's do the same about the second circuit. Call it test 2. And we'll run it. So now we're running along. It'll still take the same amount of time, but we've also output some information. So let's look at what we output. So we'll go into source, source, and we're in the release directory. So here's everything we've done so far. And there's now a test1.htm and tech, and a test2.htm and tech. So we take test1.htm and look at it. And gee, there's our gate with the rotation angle that we used. Here are the control knots between the other gates. And here's the measurements that generated classical bits. If we take a look at test 2, we'll see that all the C knots got collapsed together into one matrix, which is why this ran so much faster. And the system will do all sorts of optimizations for you, but this is a good feel for how it works. Also, while we've been running, we've been getting a log file called liquid.log. If we look at the log file, what we'll see is here's our show of test 1, and then the dump. There was a sequence of applications of gates, where the first gate was our Rx of 0.79. It's a rotate X. This was our help message we put in the gate. This is the actual unitary matrix that was generated, and the entire circuit was called on all 10 wires. It's actually only operating on the first one. The next gate is a C0. Here's the C0 matrix, and it's on wires 0 and 1, wires 0 and 2, 0 and 3, and so forth, all the way down. And then finally, a measurement, which is, from the unitary point of view, just an identity matrix. It's a non-unitary operation. There could be more information if this was a joint measurement. And it's on wires 0, 1, 2, 3, 4, 5, 7, 8, 9. So, what about test 2? Well, test 2, the rotation looks identical, but now all the C0s are replaced with a single gate, where the system generates a name for it, and then these are all the non-zero entries. It's a sparse matrix. And these are all the non-zero entries in the matrix. So this is a fairly big matrix. The indices are in hex, just to make it easier to output. And then the measurements look identical. So that's what the log file looks like. So you can put a lot more information into the log, and you actually put things directly in the log without putting them on the console when you have large amounts of output. So let's switch gears a little bit. Let's move over to quantum chemistry. We're now going to change directories and move into the liquid samples directory. We'll take a look at quantum chemistry. So liquid that we're going to run is sitting in the bin directory. We're going to say liquid of chem of H2. So H2 is just two hydrogen atoms sitting next to each other at a specified distance. And we'll run it. So it's already done, but it goes by really fast. So let's take a look at liquid.log. And what we'll see is we have the molecule H2. The parameters that were handed in was that we're doing a Trotter number of 32 with 28 bits of phase estimation and a first order trotterization. There's a bunch of other parameters you can set, but in this molecule there are very few terms and very few circuits generated from the terms. These are the actual constants that are read in from the files and where they're used in the terms. And then finally, we take the 87 gates that were implied by the input, show how they break down for each term, which gates of what type are available, and then we collapse all of this into a single unitary matrix. Once we have this one unitary matrix, we exponentiate it to get the 32 Trotter, and we get the 28 bits of phase estimation. You'll also notice along the way, we notice that we've drifted away from unitary. We get numerical errors as we exponentiate, and so we fix them and bring this back into unitariness as we go. Finally, we actually apply the result. At the very bottom, we're doing an arctangent optimization for the phase estimation. There are all sorts of things you can choose. This is from a paper by Savoy and Hastings on optimized phase estimation. And then the other bits, as we come up, we get higher and higher confidence in them as we go up. In this case, actually everything's 100% confidence. And we finally get a result at the end. The actual line we care about is the CSV line here. And so what I'm going to do is run it again. Let's put that away. We'll run it again. So now we'll bring back the command line we had. And I'm going to add to it a find of that CSV line. This is grep on Windows. And then I'm going to sort it by where the energy starts in column 25. So now we're running the whole thing again, but now we'll just see sorted energies coming out. And so what you see is these are the actual phase estimation, the 28 phase estimation bits that were read. We'll see that a couple of the outputs were completely wrong. They have no overlap with the initial state that we prepped the system in. But all the others look really good, and the only difference really are those bottom two bits where we're doing the arctangent approximation to get a little better accuracy. But we get an energy that is a total energy of minus 1.137, and then this is the non-nuclear energy. If we get rid of the protons, this is the energy of just the electronic part of the system. There's also more information here of any information that was in the file, what Trotter number, what Trotter order, and so forth. So this is the most useful line that you'll get from the quantum chemistry. And if we wanted to look at what the input file that Liquid used for this, we can look at h2 underscore sto 3g4.dat. And if we take a look, we see a file that has a format that's very easy for you to generate. All the fields are just a name equals, so tst equals, starting at 0, and this can be repeated, so you can have any number of molecules in the same file and just pull them out by test number. Info is a free format string that you can use for anything that goes into the CSV result. In this case, we're saying what the bond angle, there is no bond angle for H2, and the bond distance is. This is the nuclear repulsion. This is what's used to go between the two numbers here. The Hartree-Fock energy that came out of the classical quantum chemistry package, and you'll notice this energy is significantly bigger than what we got because we're doing a full configuration interaction model. We're doing a much more accurate model than came out of the quantum chemistry. And then these are the actual orbitals and their integrals that were generated. So you can use any number of packages. There are examples in the samples directory for PyQuante and for Psi4. The examples in Liquid all come currently from Psi4. If we want to look at a little more sophisticated molecule, we could look at H2O, and it has the same general format, but now there's a lot more integrals and a lot more information about the molecule. This has 7 orbitals or 14 spin orbitals that have to be specified. So now we have these files that you can generate and load into the system, and the user's manual explains how to generate your own. And if we wanted to run water, it's going to take a while, so I'm not going to pipe the output yet. We'll just say run H2O. The system will read it in. In this case now we have 15,000 gates, lots more terms, lots more gates of different types, and now we're taking all of these and collapsing them down into a single matrix. So we collapse them all the way down, and then we're going to exponentiate and get our answers. Normally, if we didn't do this, this would take anywhere from 1 to 2 hours to get us one solution for water. This way, we get the first solution out very quickly, in about half a minute, and we can get any number of solutions we want, one after the other. And so there's our answers. So for example, we're getting a total energy of minus 75.7286 and so forth. So this is pretty good. We're able to do various molecules. You can actually add your own to the system. And what I'd like to do now is to show how we can do all this from a scripting level, because then you can write automated scripts to do a lot of this. So what I'm going to do is open up h2.fsx. I'm going to edit. And let's just close everything else and look at this file. So this is an example. The FSX files in the samples directory are good examples of how you can write code to automate Liquid. And the main piece is there's always a script module, and the script module is where you put your code. Quantum chemistry uses a dictionary of strings to set all its parameters. So for instance, what test number, how many bits of phase estimation, what Trotter number, and alike. All of these are documented in the user's manual. And instead of loading a data file, we're going to do it right in line by putting data for each test, one after the other here, in an array, instead of putting them out in an outside file. So this is fully self-contained. And then just like we had when we programmed in Visual Studio, we put a liquid attribute in front of the things we want to call from the command line. In this case, we're defining two functions. One is called test, and one is called trot. Test sets which test number we want to run, and trot uses a default test number, but overrides the trotter number with whatever trotter number we want to use. So now we can run Liquid, just like we did. But now we're going to say load the script for h2.fsx. So that gets it loaded into the system. It will load it, compile it, output a DLL, and then load that library back. So this will give us a library we will run off of. And then we have to tell it what to call. So we're going to call our test function, in this case, of test number 26. And again, I'm going to pipe that to a find of CSV, and pipe that to a sort of plus 25. So now we compile the script, we run the script, we go do everything we did before, and we really have the same code we had before, and sure enough, we get the same answers. Everything looks pretty good. Now we're going to alter it by saying, you know, we already just compiled this DLL. Why don't we just load the DLL? It's already sitting there. Why compile it again? And so this time, instead of compiling the script, boom, we just ran the DLL. And after compiling, you don't have to do it every single time, even though it's a script. To show you the difference in numerical output, I'm going to change this to the trotter call and say do a trotter of 2, which is a very bad approximation for the system. And now you notice the energies that come out are much bigger than the energies we had at our trotter of 32. And we can go the other way. We could say let's do a trotter of 1024. And now we get even lower energy than we had at trotter 32 as we're slowly getting closer and closer to the exact ground state, or as close as we can get with this model. So that's a good example of the types of things you can do with some of the built-in software. For more information, I suggest going into the docs directory and taking a look at liquid.pdf. This is a 100-page user's manual that contains all sorts of information for the system. If you take a look through the table of contents, you'll find we have all sorts of information on basic operation, how to write code, extending the simulator, how to manipulate circuits, doing quantum error correction, advanced noise modeling, the Hamiltonian modes for both first and second quantized Hamiltonians, and then all the built-in samples are documented as well. When you're writing code, it's useful to have an API manual, and in the same directory is a liquid.compiled help file, a chum file. And here's all the information on what we were using, and in fact, if we go into circuit, which we called a few times, there's the circuit compile call that we used. Here's the grow gates call and the various options. If we go to grow gates, it says it takes an option of a grow parameters. Go into grow parameters. This is all MSDN style documentation. There's over 700 pages of documentation of all the various APIs. And that's probably enough to get started with. There's also online API documentation on the GitHub site. And I suggest using the GitHub site for interacting with other people and putting up source code for people to see, as well as using the listserv. Make sure you're registered so that you get notification as we add things to the system and as we do workshops and make things available. And thank you for your time.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.